Today we have a talk by a new member of our lab, Veronika Kikteva. So Victoria, please.
I'm sorry, but Veronika.
Veronika. I'm sorry.
Can you see my presentation?
Yes, we do.
Thank you. The theme of my talk is the Commuting Derivations Conjecture. My talk is based on the work of Stefan Maubach. We denote such way a polynomial ring in n variables. And we denote such way the set of all locally nilpotent derivations on polynomial ring. Then we say that a polynomial f is a coordinate if there exist f2, etc., fn polynomials such that polynomial ring in f2, etc., fn's over C is a polynomial ring in n variables. So there are some necessary conditions for f being a coordinate. The first, f plus alpha should be irreducible for all complex alpha. Then ideal generated by partial derivations with respect to x1, xn should be an ideal generated by 1. It is true because Jacobian of automorphism that maps x1 to f and xe to fe is a non-zero constant contained in the ideal E. So we can make an expansion of it along the first row and get that non-zero constant belongs to ideal E. Then the third necessary condition is that polynomial ring in n variables factorized by ideal generated by f is isomorphic to polynomial ring in n-1 variables. Then the fourth is that there exists a subring A such that f is algebraically independent over A, and polynomial ring in f over A is polynomial ring in n variables, and A is isomorphic to polynomial ring in n-1 variables. So there are some conjectures.
Oh, Veronika, I'm sorry. Firstly, there is a question by Boris. Please look to the chart.
This is an ideal generated by polynomials. So yes.
And maybe a short comment from myself. I think that everything is very well explained, and all people either knew before or understand just now that what is a variable or what is a coordinate. Some people call it variable, but it's more correct to say coordinate. But this is very non-trivial notion. So the question about is a given polynomial a coordinate or not, this is the question, may we map, I don't know, first coordinate x1 in our polynomial ring by some automorphism to this polynomial f. So is it an image of the first generator under some automorphism? And given a polynomial f, it is very difficult to say whether it's a coordinate or not. Certainly, there are some conditions. If it is not a reducible polynomial, then it is definitely not a coordinate. If it can be made reducible by adding some constant, certainly this is not again a coordinate. And also other conditions which are given on the slide, they allow to prove that some polynomial is not a coordinate. But if all of them are fulfilled, then it becomes a difficult problem. I don't know whether you will discuss this in this talk, but this is quite active research area to characterize coordinate in the polynomial. Okay.
The conjectures. The first is Abhyankar-Sataye conjecture. It says that if f is a polynomial and polynomial ring in n variables factorized by ideal generated by f is isomorphic to polynomial ring in n-1 variables, then f is a coordinate. The second conjecture is Cancellation Problem. It says that if polynomial ring in T over A is polynomial ring in n variables, then A is isomorphic to polynomial ring in n-1 variables. And the third conjecture is commuting derivations conjecture. It says that if D1, etc., Dn minus 1 are locally nilpotent derivations, they are linearly independent and they are all commuting, then intersection of their kernels equals to polynomial ring in F, where F is a coordinate. So these are results of work by Stefan Maubach. The first part, it was proved commuting derivations conjecture in case n equals 3.
I'm sorry, but as far as I understand, this commuting derivation conjecture is a central point for your talk. May you go back to the previous slide?
Mm-hmm.
So let us think a little bit. What does it say? May you comment somehow on this? What do you need to comment? Everything is written, I understand. But nevertheless, let us try to realize somehow what is it about. So given a collection of n-1 linearly independent LND, which pairwise commute.
It seems that when we intersect kernels of LND, it can be believed that the algebra, which is intersection, is of dimension 1. But what is non-trivial that it is a polynomial ring over a coordinate.
But let me think a little. So when you go from some domain to the kernel of a locally nilpotent derivation, then dimension of crude dimension of the corresponding domain always decreased by 1, right? So you took first local nilpotent derivation, take it kernel, it has dimension n-1. Then you restrict the second derivation to this kernel. You can always do it because they pairwise commute all derivations, right? You obtained a local nilpotent derivation on the restriction, then you go to this kernel, and this has dimension n-2. And continuing this line of discussion, we obtain that the intersection of all n-1 kernels is a domain of dimension 1, right? And this is a subalgebra in the polynomial ring. So is it clear that this is something rational, or what can we say about this?
It will also be algebraically closed, since it is
algebraically closed inside of the polynomial ring.
Yes, one-dimensional algebraically closed ring, and it will be a UFD probably.
Mm-hmm.
I'm sorry, I don't understand. One-dimensional, it is in the sense of linear algebra, or it is something?
In the sense of a crude dimension.
In the sense of crude dimension. When I speak about dimension of the algebra, this is a transcendence degree. This is a maximal number of algebraically independent elements.
Thank you.
So in other terms, this intersection is an algebra of functions on some curve. Am I right that this is clear, that in the one-dimensional case, this is finitely generated?
It's a little bit problem which would be later, because there is a link that it's finitely generated, but we have not managed to obtain this link, and we have not understand why something is finitely generated. But it is a particular case of 14th Hilbert's.
May I comment? I think it follows from certain results of probably Abhyankar or something, that this will be C1. If it is one-dimensional as a ring and algebraically closed and UFD, it will be C1. I mentioned this result during my talk probably, but the thing is, suppose it is C of some F, whether that F is a coordinate or not, that is non-trivial.
So by some standard arguments, we can understand that this intersection of kernels is the algebra of polynomials in one variable.
One variable, but whether that generator is a variable in the bigger polynomial ring, that is a question.
The problem is whether this is generated by coordinates. Okay. Okay, so let us go further.
Results. The first, as it was said, is a commuting derivations conjecture in case n equals 3. And then there will be a theorem that if Abhyankar-Sataye conjecture for n-1, commuting derivations conjecture for n, and the cancellation problem for n-1 are true, then we can describe all coordinates of such form. And the third part, there are conjectures about possible generalizations of the concept of coordinate for elements of general rings are made. So
this 3 points here, this is your plan, what you will discuss below, or what is it?
Yes, it is my plan, and it is a plan of article by Stefan Maubach.
Mm-hmm.
Let's start a proof of commuting derivations conjecture for 3. The first lemma, it says that if A is a C domain, which means that it is a C algebra, which is a domain, and D1, etc., Dn are commuting locally nilpotent derivations, such they are linearly independent over A. We define the restrictions to the kernel of Dn, and then delta 1, etc., delta n-1 are linearly independent over kernel of Dn. We can observe that delta E is well defined because for all A from kernel of Dn, we have that since dE and Dn are commuting, this equals to 0, and we see that dE of A belongs to the kernel of Dn. So it will be invariant under the action of dE. The proof of lemma 1, we suppose that this linear combination equals to 0 for some AE from kernel of Dn. And since Dn is a non-zero locally nilpotent derivation, there exists a preslice for Dn. It means that there exists P in A such that Dn of P doesn't equal to 0, but Dn in the second degree of P equals to 0. So we define D, which is Dn of P, and we define S, which is P divided by D. And we can observe that Dn of S equals to 1. So S is a slice for Dn. We say that dE acts on a polynomial ring in D to the -1 degree according to this rule. And by principle 11 from the algebraic theory of locally nilpotent derivations by Freudenberg, we have that polynomial ring in D to the -1 degree over A equals to polynomial ring in S over this ring. Then we define A, which is a linear combination with coefficients from the first linear combination. And we define A with tilde such way. So we can see that the sum of AE to the mth degree dE of S equals to D to the mth degree A, which is equal A with tilde. And since S is a slice for Dn, we have such expression. We can prove the same statement on the kernel of Dn, because on the kernel of Dn, dE equals to its restriction to kernel of Dn, and Dn equals to 0. So with our assumption, this equals to 0. And the same statement is true for D to the -1 degree. Here we use a rule from the previous slide. And we use that D is in the kernel of Dn. And we use our assumption again. So it is equal to 0. Now, we see that A is a subset of polynomial ring in S over this ring. And we proved this expression for S for D to the -1 degree and for elements from kernel of Dn. So it is true on A. And from the linear independence of the dE over A, we deduce that AE equals to 0. So we see that delta E are linearly independent over the kernel of Dn. So we proved lemma 1. Then lemma 2. Let A be a C domain such that transcendence degree of quotient field of A is n. And let D1, etc., Dn be commuting locally nilpotent derivations on A, which are linearly independent over A. Then, at first, there exists SE in A such that DE of SG equals to Kronecker symbol for E and G. And the second statement that A is a polynomial ring in S1, etc., Sn over C. The proof of lemma 1.
Oh, Veronika, once more. This is a somehow new style presentation in Zoom. It's not sufficient just to read what is written. Everything is written very clearly, but it's difficult to follow. May you return to the formulation of lemma 1? So what this lemma is claiming, it say just that they are linearly independent. But not over the field, but over this ring. So there is no combination of these derivations with coefficients in this ring, which is 0. You mean this? And here you gave some proof.
So here we suppose that there is combination equal to 0, and we come to that this combination is trivial. That all AE equal to 0.
AI.
AI equal to 0.
Okay, clear.
Maybe I can do some comment. It's very useful to take a localization of a ring on image of local slice or pre-slice, as Veronika note this concept. So it's a rather typical way to consider this localization, and then all idea is to prove this linear combination on the generators.
So this is based on some localization. Okay, then lemma 2. Let me just understand the claim. We have a domain of transcendence degree n, and we have the same number n of pairwise commuting local and nilpotent derivations, which are linearly independent over A. Okay, then it is claimed that this may happen only for polynomial algebra, right? So this is the second state. And for polynomial algebra, this really may happen because we have, what do we have? We have partial derivations, right? And they give us an example of such commuting family of local and nilpotent derivation. This is first, and second, that we have such specific element as I, which like variables. They will be these variables, precisely. So is it true that our derivations, d1 and so on, dn, will be precisely partial derivations of our polynomial algebra or not?
Yes.
In the coordinate system S1, S2, Sn, they will be partial.
Because they act on these generators as it should be, as partial derivations. And derivations are uniquely defined by their action on generators. So the conclusion of lemma 2 is that this may happen only on polynomial algebras, and on polynomial algebra, this may happen up to automorphism, only for one collection of such derivations, only for collections of partial derivations in variables. Okay, now the lemma is clear. How to prove it?
We will use induction on n. And in the case n equals to 1, we have that transcendence degree of kernel of D1 is 0. So the kernel is just C, and they exist pre-slice. If we denote with C D1 of P, we have that P divided by C is a slice for D1, and this is what we need.
I have a question here. Maybe I'm mistaken. This element P by C, this did not be an element of A. Suppose for n equal to 1. I think if we have only D1 and I take something, D1 is suppose fx del by del x. So do we need n greater or equal to 2 for this theorem or lemma?
Can you repeat the question, please?
My question is, suppose n is 1, suppose n equal to 1, and suppose my ring A is Cx, a polynomial ring in over X. I take D1 to be some fx del by del X. That is a non-zero LND, and so it will be, I think, linearly independent over A. Since there is no D2, there is no question of commuting. So, but for those LNDs will not have a slice.
Certainly, Nihilesh is right. This lemma is wrong for n equal 1.
Probably we have to assume n greater or equal to 2. But
Veronika, do you see what is the problem? Take polynomials in one variable. Then there are no conditions on this LND, but there are many LNDs on the algebra of polynomials in one variable. Oh, just a moment. Nihilesh, and what are LNDs for the algebra of polynomials in one variable?
They are all replicas of del del x.
But there are no replicas because no kernel.
Oh, okay. Yes, yes. So it will be some lambda times del del x.
Lemma is correct. So
yes. So C is a unit here.
Okay, no problem.
Thank you.
Excuse me, what is replica? I'm curious.
Replicas, this is when you take local and nilpotent derivation and multiply it by a polynomial which is in the kernel of this derivation.
I see, okay.
And you can produce many proportional derivations.
Yeah,
but in the case of polynomials in one variables, the kernel is just constants. And there are no non-trivial replicas of a given derivation.
We are going to the case where n is greater than or equal to. Here we have that transcendence degree of kernel of Dn is n minus 1. And according to lemma 1, derivations which are restrictions of dE to the kernel satisfy the hypothesis of the proposition. So
I'm sorry for a short comment, but I'm sorry for interruption. But I have this story. Maybe I told some of you already. I visited Germany maybe 10 years ago, and my German colleague was invited to give a talk at Shafarevich seminar. And his older German friends said him, this is a bad idea. So these Russian seminars, they are quite terrible. How these Russians do? They usually propose you to start, you formulate your theorem, and then they, 40 minutes, discuss why this theorem is wrong, how to construct counterexample to this theorem, how to prove this theorem between themselves, they don't speak with you. And only if in 40 minutes they are unable to produce counterexample or to find the proof, then they say, please continue. So our seminar now works almost in the same format, but the difference is that in this story, this 40 minutes discussion should be in Russian. And now we try to have this discussion in English. So this is the only difference. Okay, so let us discuss the proof.
So we use the assumption of induction, and we say that for the first n-1 derivation, there exists Si such that this is true. And the second statement is, and here's the second statement. We say that Si belong to the kernel of Dn, and because of induction, we have that dj on Si equals to 0 if I doesn't equal j. And this was for first n-1. And similarly, Dn has a slice Sn in the kernel of D1. Then the second statement follows from this fact, and the fact that A is a polynomial ring in Sn over the kernel of Dn. So we have that A is a polynomial ring in S1 Sn over C. So we have proved lemma 2. Then lemma 3. Let A be a C domain such that transcendence degree of quotient field of A is n, and D1, etc. dp are commuting locally independent derivations such that they are linearly independent over A. So we have that transcendence degree of quotient field of intersection of the kernels equals to n-p. Again, we use induction, and the case p equals 1 is well known. Then we should consider a case when where p is greater than or equal to. We denote with b the kernel of dp, and by lemma 1 derivations delta e, which are restrictions of de to the kernel of dp, are linearly independent over b. So we use induction here. We have that transcendence degree of quotient field of intersection of kernels of delta E in B equals to transcendence degree of quotient field of B minus P minus 1. So we have that it equals n minus P. And then the result follows from the fact that this intersection equals to intersection of kernels D1, dp in A. So we have proved lemma 3.
I think that there are no need of comments. Lemma 3 is quite obvious. That when we intersect kernels, our transcendence degree or dimension decreases by 1. Okay, quite predictable.
So if A is some ring, we denote by A star the set of invertible elements of A. Then lemma 4. If A is affine C domain with transcendence degree of quotient field equals to n, and invertible elements of A are non-zero constants, then if A is a unique factorization domain and D1 etc. dn minus 1 are commuting locally independent derivations on A which are linearly independent over A, then the intersection of the kernels is generated by G for some G in A which satisfies that G minus C is reducible in A for all complex C. So,
so this is what we discussed at the beginning, that it is clear that the intersection of kernels will be a polynomials in one variable. And even this variable is not arbitrary, this is quite specific, such that G minus C is irreducible. But since it's not clear that this is a coordinate.
Mm-hmm.
Okay, so let us prove this lemma.
We put B for the intersection of kernels of DE. And by lemma 3, we have that transcendence degree of B equals to 1. Also, B is a unique factorization domain. It is true because if we have the product of AB in kernel of D, then the degree of AB equals to degree A plus degree B equals to 0. So we have that the kernel of DE is factorially closed in A. And for A in kernel of DE, if we have A equal to BC in A, then B and C belong to the kernel of DE. Then irreducibility in A is equivalent to irreducibility in kernel of DE. So following this procedure for every derivation, we come to the conclusion that B, which is an intersection of kernels, is a unique factorization domain.
So let us stay on this. I hope that all participants of the seminar already know some basic fact about local nilpotent derivations. Then say if you take a local nilpotent derivation and you take its kernel, then the transcendence degree is one less. This we already use. This is another property of local nilpotent derivation. Its kernel, this is some subalgebra. This is quite specific subalgebra. This subalgebra is factorially closed. It looks like a very strong condition. Then if a product of two elements in big algebra belongs to this subalgebra, then in fact both factors are in this subalgebra. And this condition, this is elementary to check with these degrees. This is written in Freudenberg book, no problem. And this implies that this passage to the kernel preserves the property to be a unique factorization domain. Why? This is written here. Because if you have in a big domain unique factorization property, if you have that some element is a product of primes, and this element is in the kernel, then all primes in this product are also in the kernel. And so we have this unique factorization as well. So say you start from some unique factorization domain, something simple like polynomial algebra. You go to the kernel. It may be quite complicated, the structure of this kernel. But in any case, this is a unique factorization domain. And this is important to know. Okay.
Then we can observe that B is equal to intersection of A and quotient field of B. It is true because if we have A from A equals to B1 divided by B2, which are from B, then we have that A multiplied by B2 equals to B1, and from the fact that B is factorially closed, we have that A belongs to B2. So there we use the special case of 14 problem of Hilbert. We use that B is normal since it's a unique factorization domain. And we have that B is a finitely generated C algebra. So B is an affine domain of dimension 1, and it's a well-known result that if invertible elements of B are non-zero constants, and B is a unique factorization domain and an affine domain of dimension 1, that B is polynomial ring in G over C. So since G minus C is irreducible in a polynomial ring in G, and B is factorially closed in A, we have that G minus C is also irreducible in A. So we proved Lemma form.
So here I don't understand something. Okay, we know that this field, quotient field of B, has transcendence degree 1. It means that there is only one algebraically independent element, and any second element is dependent with this element. Okay. It is written that this is a special case of Hilbert 14. What is Hilbert 14? It's not clear. Maybe Hilbert 14's problem, but this is a problem. This is not a theorem. And I don't understand how do we conclude that B is finitely generated.
I think it's Hilbert's 14th problem.
This is a problem.
And I think if you go back to the previous page, I think you have written B is A intersection QB. This should be finitely generated. If you look at the statement of the Hilbert's 14th problem, I think for the low dimension case, this is the statement, and the problem has been proved in the affirmative.
Yes, Nihilish is right. So let me say it again. For me, Hilbert's 13 problem, this is a question whether the algebra of invariance of a linear group is finitely generated.
Yes,
But this is not original formulation. Hilbert asked another thing, exactly as Michilich said. Hilbert asked, if I take some domain, which is finitely generated, say algebra of polynomial, and you take some subalgebra, and take the quotient field of this subalgebra, whether the intersection is finitely generated. And the question about the algebra of invariance, this is a particular case with this question. And Hilbert's idea was that the answer is positive in this general case. And it was some wrong proof by some mathematician with name Maurer, but then it turns out that there is a mistake in this proof. And then it turns out that even the case of algebra of invariance, even in this case, the statement is wrong. So the answer is negative even for the particular question. But in low dimension, as Michilich correctly said, the answer is positive. So if transcendence degree is 1, then it is finitely generated. I don't remember what is the reason for this. There should be some easy reasons. Okay, but this is an exercise. Okay, then it's clear. So it is finitely generated. And this is so this is the algebra of regular function and some affine curve. This curve has only constant invertible functions. And this is a unique factorization domain. So it has only principal divisors. The divisor class group is 0. And this may happen only for rational curves. So we conclude that if a rational curve has only invertible functions, then this is a line. Okay, at least for me now the arguments are clear. Okay.
So we are going to Lemma 5.
No. And this last statement concerning irreducibility, let me think. Since this element is irreducible, because this is a polynomial algebra. So for this algebra, it is clear. And the same is true in the big algebra A, because irreducibility is preserved when you go to the to the kernel of the derivation. Okay. Yeah.
So Lemma 5, it says
how many lemmas do you have?
Here 5, and in the second part 7.
Okay, so
but some of them are small. So let D1 and D2 be two linearly independent commuting log linear Nilpotential derivations. Then there exist G, a polynomial which is not constant, such that the intersection of kernels generated by G and localization localization of polynomial ring E at B of G equals to localization of polynomial ring in FGP at B of G for some polynomials F and P and non-zero polynomial B of G. Then the third statement is that polynomial ring in X, Y, Z factorized by ideal generated by G minus lambda is isomorphic to polynomial ring in two variables for all complex lambda such that B of lambda doesn't equal 0. So
it's best to feel alone. Sergey, maybe you may comment. What does this lemma mean? It means what is written, I see.
Sorry, let me think about it. Okay, there is a I don't know how to comment this lemma.
The first point is clear. When you intersect two kernels, you obtain polynomials in one variable. This we already know from former lemmas, right?
Yes. And the second part is as follows. If you have a kernel of an LND in polynomial ring on 3 variables, then non-trivial Majanishi theorem that it is isomorphic to a polynomial ring in 2 variables. So F and maybe G are generators of the kernel, but it is given in the proof. And P is just a local slice. And when you take a localization in, I'm sorry, G is a local slice, and F and P should be kernel, something like this. And when you localize the ring on the image of local slice, then it obtained that these two rings are equal. I don't know how to comment it in better way.
Okay, if no comments, then let us go to the proof.
As it was said,
And what is B?
B of G is a polynomial. We will define it later.
Okay.
No, but what is the statement? For any polynomial B, for some polynomial B?
There exists a polynomial B.
So for some polynomial, okay.
So we use Meniche theorem, and we say that the kernel of D1 generated by F and G, and the kernel of D2 generated by P and Q. And since D1 and D2 compute, we have that the kernel of D1 is invariant under the action of D2. So here is an explanation. So we can define a restriction of D2 to the kernel of D1. And by lemma 1, it follows that D2 doesn't equal to 0 on the kernel of D1. So by Rechler's theorem, we may assume that D2 is a polynomial A of G, partial derivation with respect to F. Which means that D2 of G equals to 0 and D2 of F equals to A of G. So now we have that intersection of kernels of D1 and D2 is a kernel of restriction here in a kernel of D1 and is generated by G. So,
Veronika, can you formulate Rechler's theorem?
There exists an automorphism that our locally nilpotent derivation can be mapped to derivation that has such a look.
The formulation is as follows. This is a complete description. This is, as far as I remember, 60s. This is quite old theorem. This is a complete description of locally nilpotent derivations for polynomials in two variables. Up to automorphism of this ring, any locally nilpotent derivation is a replica of partial derivation. This is a state.
So here we proved the first statement, and now we get the same for the first derivation. We say that the kernel of second derivation is invariant under the action of first derivation, and we put D1 for the restriction of first derivation to the kernel of second. And again, we use Rechler's theorem, and now we may assume that D1 is a polynomial B of Q, partial derivation with respect to P, or some non-zero polynomial B of Q. So now we see that the intersection of kernels of D1 and D2 is a kernel of this restriction in the kernel of D2. And it is generated by Q. Here we had that it is polynomial ring in J, and here it is polynomial ring in Q. So we have that G equals to lambda Q plus mu for some non-zero lambda and mu complex numbers. Now we replace Q by G. And such a polynomial b of q by b with tilde of g. And now we may assume following. The kernel of D1 is generated by f and j. F and j are in kernel, and D1 of p is b of g, which is not equal 0. And then the kernel of D2 is generated by p and again g, and p and j are in kernel, and D2 of p is a of g, which is not equal to 0. Then we have that polynomial ring in f, g, and p is isomorphic to polynomial ring in 3 variables. It is true because if f depends on f and g, then we have that d1 of p equals to 0, but here it is not true. So we observe that d1 of p doesn't equal to 0, and d1 to the second degree of p is d1 of b of g, and it is equal to 0. So if we denote with s p divided by b of g, we have that s is a slice for d1. So we have that localization of polynomial ring in xyz at b of g equals to polynomial ring in S with over such localization, and this equals to localization of polynomial ring in FGP at B of G. So we proved the second statement, and now we are going to prove the third. We have that G minus lambda is irreducible in polynomial ring in f and g for all complex lambda. And since we have that kernel of D1 is factorially closed, it follows that G minus lambda is irreducible in polynomial ring for all complex lambda. Now, as it was in the third statement, we assume that b of lambda doesn't equal to 0, which means that g minus lambda doesn't divide b of g. And we denote with a polynomial ring factorized by ideal generated by g minus lambda. So we are going to prove that a is isomorphic to polynomial ring in 2 variables, and according to Lemma 2, it is sufficient to show that overlined D1 and overlined D2 are linearly independent. We say that overlined means modulo G minus lambda, according to this rule. And we suppose we suppose that A1 and A2 are such that overlined A1, overlined D1 plus overlined A2 D2 equals to 0. Then we have that an image of such a linear combination in a polynomial ring is a subset of ideal generated by G minus lambda. So in particular, we can put here P and see and use that D1 of P equals to B of G and D2 of P equals to 0. So we put here P, and we see that here this linear combination, it equals to A1 B of G, and it belongs to ideal generated by G minus lambda. Then since G minus lambda is reducible and G minus lambda doesn't divide B of G, it follows that G minus lambda divides A1. So it means that overlined A1 equals to 0. So we had that overlined A1 D1 plus A2 D2 equals to 0. So we have that overlined A2 overlined D2 equals to 0. This what it means. So if G minus lambda doesn't divide A2, then G minus lambda divides D2 of X, Y, and Z. So in this case, let E be the maximal such that G minus lambda to the E degree divides D2 of X, Y, and Z. Then we replace D2 by D2 with tilde, defined such way. And it follows that D1 overlined and D2 overlined with tilde are independent over A. And derivations D1 and D2 with tilde have the same properties as the pair D1 and D2. So the intersection of kernels of D1 and D2 is intersection of kernels of D1 and D2 with tilde. So this concludes the proof.
Just for me, this is quite difficult to follow the proofs, but I have a question to Kirill. Kirill, do we put also presentations together with video records of our seminar?
Presentations where?
Slides on the side of our seminar.
No.
I would recommend to put also separately video record and presentation, that if we would like to follow such proofs, we can look to the presentation again.
I was thinking how to comment this lemma. Maybe now I'm able.
After the proof, you are ready to comment the statement. Okay.
Yes, yes.
So let us go to the statement.
You have two these derivations. The statement is that you can intersect kernels of this derivation. Each kernel of locally nilpotent derivation on polynomial algebra in 3 variables is a polynomial algebra in 2 variables. So you can intersect this two polynomial algebra in 2 variables containing in polynomial algebra in 3 variables and obtain a polynomial algebra in 1 variable. Another way, this is something like, I don't know, Makar-Limanov invariant, but just for two derivations, intersection of kernel. But you can consider something like Dexon invariant, the algebra which is generated by these kernels. So you have two algebras, polynomial algebras in 2 variables, containing in polynomial algebra in 3 variables, and you generate by them also a polynomial algebra in 3 variables, but not exactly the same. But when you localize with polynomial from the intersection, you obtain this big algebra and small algebra in 3 variables have the same localization. I don't know whether it's useful, but
when you localize by some element of the common kernel, right?
yes, but some element of the kernel.
Mm-hmm. Okay, maybe this explains the meaning of this lemma.
So we have proved this statement for all lambda such that b of lambda doesn't equal to 0. So now we are going to lemma number 6, which says that if
stop, it was promised that in the first part there will be 5 lemma.
There will not be proof of this lemma. So if this statement is true for all but finitely many lambda in complex lambda, then f is a coordinate. So this proof follows from the work by Kaliman. And so
this is a deep statement. You don't include proof because proof is difficult, right?
Yes.
Mm-hmm.
And so we have proved the commuting derivations conjecture for case n equals 3. If D1 and D2 are linearly independent, computing locally nilpotent, then the intersection of their kernels is generated by G, and G is a coordinate in polynomial ring. So this was the first part of my talk, and At the second part, I'm going to prove theorem 2. We assume Abhyankar Sataye in case n minus 1, commuting derivations conjecture for n and cancellation problem for n minus 1. And we define f such way where p of x doesn't equal to 0. Then these statements are equivalent. The first, f is a coordinate in polynomial ring in n+1 variables. Then polynomial ring factorized by ideal generated by f is isomorphic to polynomial ring in n variables. The third, this Q of a and that one, etc., that n minus 1 is a coordinate for every a which is a 0 of p of x. And the fourth equivalent statement is that f is a coordinate of a polynomial ring in x in a polynomial ring in n+1 variables.
So what is the purpose of this theorem 2? This is a characterization of coordinates, right? Some conditions to be a coordinate.
This is a characterization of coordinates in such forms.
For a very specific polynomial, so this form.
Yes.
Right? And this is a conditional theorem. So it holds only when some conjectures are true. So
yes.
For which n it works? Say Abhyankar Suzuki conjecture holds for which n? It is proved.
It was proved for 2 and
or n equal to 3, generally it's open. Abhyankar Sataye. And I will also want to comment the talk which I gave on Asanuma threefolds, the counter example. That polynomial is of this type, but we worked in positive characteristic. Here, if you take px to be x to the power m and qx, and there are z1 and z2. So that boils down to that kind of polynomials. So this is, you can say this is a generalization of Asanuma threefolds.
So these polynomials are interesting because in the case of positive characteristics, they give some important counterexamples.
Exactly.
And this is the reason why do we consider them here. Veronika, may you return to the formulations of these conjectures? CD we already remember, but other two, Abhyankar Sataye.
It is Sataye, Abhyankar Sataye.
Sataye, I don't know how to pronounce correctly the name. And cancellation problem.
It's something like non-trivial line, if I remember correctly, from Nicholas' talk.
Yes, yes. But non-trivial lines won't be there in characteristic 0. So they will be coordinates. So that was the only obstruction.
So applications of this conditional theorem are very restricted because we know this conjectures only for very small n. Okay, but nevertheless, let us go to the proof. Okay.
The first statement follows from the fourth because it is a weaker statement in general, such as the second follows from the first. Then we will prove following 3 from second and 4 from third. We denote such way the nil radical of some ring R. And the following lemma was proved in the work by Edo and Pinero. Let A be a ring and let P be an element of A which is not a zero divisor. And let A be an element A and polynomials G and F in polynomial ring in X over A, such that F is a coordinate and A modulo ideal generated by PA is invertible, and G of X modulo ideal belongs to the nil radical of polynomial ring in X over such ring over such with such coefficients. then a polynomial of such form is a coordinate in polynomial ring in x, and y. Then Lemma 2, it was proved in work by Rossum. It says that if R is a polynomial ring in n variables and H1 extra Hk are polynomials in X, assume H1 Hk is a coordinate system when considered as an element of such localization, such polynomial ring for every maximal ideal M. Then H1 etc. Hk is a coordinate system in a polynomial ring in X over R.
Veronika, I'm sorry, we discussed this lemma just before you talk. It seems that this formulation, this statement is not understandable. It seems that H1, Hk should belong to R from K variables. And the statement is that
it might be a part of a coordinate system.
Yes. What does it?
It means that suppose if I take a K has to be lesser or equal to n, of course. But if you maybe you can extend H1, H2, Hk to Hn maybe.
So it seems that you have a polynomial ring in many variables over R, and you have some polynomials, and then they are coordinate system or partial coordinate system when for any maximal ideal it is true for localization. I'm sorry, I don't know whether all participants have understand, because here I don't understand some lattices. For example, what is in the power K?
I think that it is just like a product. So if we will use this lemma only in case k equals 1. So we can say that H1 is if H1 is a coordinate in a polynomial ring in X over localization for every M. So then H1.
I think that X is a multi variable. So X is not just one variable. It's X1, Xk. So otherwise, there is no concept of coordinate system of polynomial ring in one variable, just one polynomial. There should be many variables. Maybe this notation K should understand that it is polynomial ring in K variables. I don't know. So
yes, it has to be.
The statement what you need that if we have a polynomial ring in K variable and we have K polynomials in it, and they are coordinate system after localization in every maximal ideal, then it's a coordinate system on this polynomial ring in K variable before this localization. I'm sorry, it's my fault.
But can we go further?
Sure.
Then there was a polynomial f and there was p. So we denote roots of p with alpha e such way. And lemma 3, which proves that the fourth statement of theorem 2 follows from the third. If q of x z1 zn minus 1 is such that q of alpha and that is a coordinate, then such polynomial f is a coordinate in a polynomial ring in n+1 variables over polynomial ring in x. So we use previous lemma, and we see that it's sufficient to prove that f is a coordinate in such polynomial ring over localization of polynomial ring in x for every maximal ideal m in a polynomial ring. So let m be generated by x minus alpha for some complex alpha. And notice that for a of x, which is a polynomial of x, we have that a belongs to the invertible elements of localization if and only if a of alpha is not equal to 0. So the first case, we have alpha doesn't equal to alpha e. So we have that p of alpha doesn't equal to 0. And so f is a coordinate in a polynomial ring over such a localization. Then the case alpha equals to alpha 1, we say alpha 1 because alpha equals to alpha e has the same proof. We denote q of alpha z1 zn minus 1 such way, and in the statement of our lemma, we have that q1 will be a coordinate in a polynomial ring in n minus 1 variables. Then we define p with tilde such way. It equals to p of x multiplied by x minus alpha to the degree of minus e1. And now using f equals to such polynomial, and we have that p is p with tilde is invertible element, and using lemma 1 we have that f is a coordinate in a polynomial ring over such localization. Then we have proved lemma 3. Lemma 4. Let q be the polynomial of n-1 variables, and suppose Abhyankar Sataye for n-1 and cancellation problem for n-1 are true. If polynomial ring factorized by ideal generated by q is isomorphic to polynomial ring in n-1 variables, then q is a coordinate in n-1 variables. So the proof, we have that polynomial ring in n-1, we have that polynomial ring in y with coefficients of this factor ring is isomorphic to polynomial ring in n-1 variables. So by cancellation problem for n-1, we have that this factor ring is isomorphic to polynomial ring in n-2 variables. And by Abhyankar Sataye for n-1, we have that q is a coordinate in polynomial ring in n-1 variables. Then we proved lemma 4, lemma 5. Let R be a domain and R in R such that ideal generated by R is a prime ideal. Then we have that R is irreducible in R. without proof. Then lemma 6. Again, we define f such way, let f be reducible. Then there exists such complex lambda that x minus lambda modulo f is irreducible in such factor ring. So we take lambda such that p of lambda doesn't equal to 0. Then we have that polynomial ring factorized by ideal generated by f and x minus lambda equals to polynomial ring generated by this polynomial, which is isomorphic to polynomial ring in n-1 variables. This is a domain, so ideal generated by x minus lambda and f is prime. So we have that x minus lambda modulo f is irreducible by the previous lemma. And lemma 7, where we shall prove that the third statement of theorem follows from the second. We assume cancellation commuting derivation conjecture for n, cancellation problem for n-1, and Abhyankar Sataye for n-1. We have such a polynomial, and we assume that polynomial ring in n+1 variables factorized by ideal generated by f is isomorphic to polynomial ring in n variables. Then for every a which is 0 of p of x, we have that q of a z1 zn-1 is a coordinate. So the proof of lemma 7. We define derivations dE such way, and we see that they are triangular, since, for example, dE of y is a partial derivation of q with respect to ze, which belongs to such polynomial ring. Then dE of zj equals to 0, dE of ze equals to minus p, and p is a polynomial of x. So it belongs to this ring. And we have that dE of x equals to 0. So now we have proved that these derivations are triangular. And we know that triangular derivation is locally nilpotent. Then we have that these derivations are commuting, and they are linearly dependent. Then we have that since dE of f equals to 0, we have that dE on ideal generated by f is a subset of ideal generated by f, so it is invariant. So if we define overlined derivations such way, they will be well defined, and also they will be independent. We assumed commuting derivations conjecture, so we have that intersection of kernels of overlined dE is generated by G, where G is some coordinate. So here we have that x belongs to the kernel of every dE. So we know that polynomials in x belongs a subset of the polynomials of G. Here it is. And by previous lemma, we have that x minus a is irreducible in this factor ring for some complex a. And now we denote with q of g x minus a for some polynomial q. We decompose q into linear factors t minus lambda e, and observe that g minus lambda e, since it is a coordinate in such factor ring, it is irreducible here. So it follows that g minus lambda, which are here, divides the irreducible element x minus a. So we have that x minus a equals to bg plus c for some non-zero b and c complex constants. So now we have that polynomials of g are equal to polynomials of x, and x minus alpha is a coordinate in a polynomial ring in n+1 variables factorized by ideal generated by f for every complex alpha. So we use it. We have that polynomial ring in n-1 variable is isomorphic to polynomial ring in n+1 variable factorized by ideal generated by f and x minus alpha for all complex alpha. Then in case that p of alpha equals 0, we have that this polynomial ring is isomorphic to polynomial ring in n variables factorized by ideal generated by q of alpha z1 etc. zn-1. Then we use cancellation problem for n-1, Abhyankar, Sataye for n-1, and Lemma for, and we have that q of alpha z1 zn-1 is a coordinate. So now we have proved Lemma 7 and the main theorem of second part. So the third part of my talk is an extension of the concept of coordinate. We say that polynomial f is a stable coordinate if there exists such natural M that f is a coordinate in a polynomial ring in n+m variables. So here is the first approach of extending the concept of stable coordinate. If ideal E is generated by f1 etc. fm and R is a polynomial, we say that R plus ideal E, which is an element of this factor ring, we say that it is a generalized coordinate in this factor ring if such linear combination plus R is a stable coordinate. So this definition doesn't depend on the generators of I, as we will prove in this lemma. If ideal I is generated by f1 etc. fm and it is generated by g1 etc. gl, and I is a polynomial, then the first linear combination can be mapped to second linear combination by an automorphism of polynomial ring in n+m+l variables. So,
Veronika, I'm sorry. For the second part, when you had this technical conditional theorem, I gave up. It was difficult to understand. Now you come to the third part. I want to understand what happens. So the notion of a coordinate is important, natural, but difficult. And you or the author of this paper introduce new concept, stable coordinate, generalized coordinate. It will be simpler to deal with. What is the idea of this new definition?
There are only some conjectures, so there will not be such a technical part.
The concept of generalized coordinate is polynomial rings, but for other rings. So this is attempt to have a concept of coordinate of non-polynomial ring. The concept of stable coordinate, I don't know. It's very similar for stable tame optomorphism or something else.
But there is a bad news. There are no coordinates in the non-polynomial ring. There are generators, but there are no coordinates.
But there are generalized coordinates which author introduced.
Let me understand what is a generalized coordinate. This is some element of the Gaussian ring such that what? Such that we have, it's not clear how it is connected. So you have if, look at the definition. You have if, and after this if, you have no ideal. So the original, the left-hand side depends on ideal I, but in the right-hand side, there is no I.
There is, it depends on generators. I. But the lemma follows that it's not depend on generators.
It depends only on the I itself. As to me, strange, but okay.
To prove this lemma, we denote this linear combination with F and this linear combination with G. And we will show that there is an automorphism that maps F to G. Since ideal E generated by Fe and by Gi, we have that for every Gi, we can write this linear combination of Fe. Then we write for Lj this linear combination of Ze. And we can notice that G equals to the sum of FELE plus R. Now, let phi be an automorphism that sends YG to the YG plus LG and leaving other variables invariant. Then we have such statement. Here we use the definition of F. So here it is. Then we use definition of phi, which sends YG here. And then we see that this linear combination is F, and other linear combination can be written from here. So this equals to F plus G minus R. In the same way, we can make an automorphism that sends G to G plus F minus R. So F can be mapped to G by tau to the -1 degree composed with phi. So we proved lemma, and now there is a conjecture about this concept. If E is an ideal in polynomial ring in n plus m variables, and R is an element of a factor ring is a generalized coordinate, then a polynomial ring in n plus m variables factorized by E is isomorphic to polynomial ring in n variables. Then R is a stable coordinate. Then there is a second approach of extending the concept of stable coordinate. We say that if R is a finitely generated algebra, then element of R is a slice if there exist locally nilpotent derivations such that on this element it equals to 1. And we say that element of our algebra is a stable slice if there exists some natural n and locally nilpotent derivation on the polynomial ring in T1 strati n over R, such that D on S equals to 1. And there is a conjecture about this definition too. Let ideal generated by F1 extra Fm be, let S be a polynomial, then S is a stable slice in factor ring if and only if S plus this linear combination is a stable coordinate in polynomial ring in n plus m variables. And the last conjecture saying that these two approaches are equivalent. It says that if S is a polynomial of in x1, etc., xn, then the statements that S is a stable size and S is a generalized coordinate are equivalent. So that's all.
Me personally, I don't like the third part because there are only conjectures, they don't look natural, and I don't understand what was the reason to make these definitions. But maybe somebody has other opinion.
I don't know, it's new for me. I don't know whether there are examples of stable coordinate which is not coordinate. It seems that such example should be very interesting, but
yeah, I think that is a research area to determine whether a stable coordinate is a coordinate. But as of now, I do not recollect any examples, but I think there are. In at least.
But to give several strange definitions and to construct counterexamples,
Yes.
it's not good. What should be a good picture? We have a concept of coordinates. This is difficult. And we introduce some new concepts, which are more approachable, which we understand how to deal with. And this somehow helps us with coordinates. And if we produce new concepts only to produce new questions, this is somehow no reason to do.
let me say, the concept of stable coordinate, it's rather interesting. For example, what is coordinate? It's an image of a variable under automorphism. Now you take a polynomial ring, you add some new variables, and you took such an automorphism that the image of a variable from the first part is in the polynomial ring from the first part of variables. Is it right that image can be new, not image under automorphism of this? It's a reasonable question, no?
Okay, this may be a reasonable question, and then it should be an answer to this question. And if we just put it as a question, then there are too many questions and no
Yes,
result.
of course, this is not very good style to say that I have many questions, but I have not no answers. But the author do this way.
Mm-hmm.
But for me, the most interesting, of course, the first part. We thinking with Nikilesh about derivations in polynomial ring in 3 variables, and we proved the first part, and after this we find this assertion in some articles, for example, in this one.
What did you prove? This conjecture?
The first part that if we have 2 commuting LNDs on polynomial ring in 3 variables, then the intersection is polynomial ring in 1 variable.
Okay. As to me, I don't know. This is a question of taste. But as to my taste, Veronika, maybe go back. The most interesting statement was at the beginning. It was maybe Lemma 2. Yes, precisely. That if you have some collection of pairwise commuting LNDs, which are in some sense linearly independent, then nice statement. Then this is a polynomial ring, and these are partial derivatives. This looks really interesting. This is not difficult, but from a static point of view, I like it. And concerning other points, not so sure. Dear colleagues, any more questions, comments?
Can I try to ask a question? So am I right to understand that if we have a coordinate, then the set of zeros must be just a thin space, no, isomorphic to a thin space?
The set of zeros?
Well,
you mean modulo that it is an affine space? Yes.
Yes. So can one give an example when we have a polynomial such that, well, I mean, the set of zeros or factor algebra is isomorphic to affine space, but it is not a coordinate.
Then you will disprove the Abhyankar-Sataye conjecture.
Yes,
Ah,
this
which
is
is
a conjecture.
Okay.
Let
Yes.
us look again to the formulation of this conjecture.
So it basically, yes, okay, I understand.
This is precisely what you asked, Anton. This is precisely this conjecture.
It is open for n greater or equal to 3 in characteristic 0. In positive characteristic, there are contradictions.
Okay, thank you.
Any more comments, questions? So I'm sorry for my criticism, Veronika, for the first talk, very nice, well prepared. Certainly some comments from you are expected, but taking into account that you are a student and this is your first talk, then it's very nice and clear, and slides are well done, and this is very important. So thank you very much. Okay, if no more questions and comments on this talk, then I would like to invite you for our next talk, which will be very soon, the day after tomorrow. And it will be taught by Roman Avdeyev. This will be about root subgroups on spherical varieties. There is some program. Roman already told us about this, but there is some new progress on this problem. And I hope that we will enjoy this.